Okay, folks, the weekend's getting a little close here. The talk's livelier. It's like, boy, Friday must be coming soon. You don't need to draw the free body diagram. You actually have this from Tuesday. But what we're going to do is talk about alternative forms of equilibrium, some other ways of actually solving the same problem. And we'll find that these tools then will be useful as we get into the more complicated structures and stuff. We're not always going to be doing a moment equation and an fx and an fy or something like that in 2D. Now, recall this is our free body diagram from the problem that we solved on Tuesday. And I think I posted that. Did I post that for? It should be on there. So, and what we did in that one is we decided we'd start off with this moment equation at A because it was nice. If I chose it there, I eliminate two unknowns because fax and fay go through A, so therefore they will not have any sort of moment arm. So, and I can get myself an equation now with just one unknown. And that's kind of the way we want to go. It's not wrong. I could take it at B, C, or anywhere else. But I may then end up having to solve simultaneous equations. So recall when we did this, I'm not going to put the units up, but so when we did this, basically we took the moment question. Oh, I got it 20 inches.
I think the second part of the equation, the 50 times 40, I believe those are 4.
Yes. I haven't had my coffee yet today, have I? All right, does it look better now? Am I finally getting there? Okay, good. So what we did is we took our moment here and realized that this 40 is acting horizontal, but it's got a perpendicular moment arm of 10. And the good eyes here caught that the 50 is merely 4 inches over from the point A there in terms of perpendicular distance to the line of action of that force there. And then FBY is going to be 20 inches away, so we were able to solve for £30 up by plugging through there. Now, what we did on Tuesday is then we went to sum of forces of x and sum of forces of y. Another alternative approach is just using two moment equations. So what we want to do is pick another place to take a moment equation, and again, try to find something that we have dimensions to and that sort of thing. In this particular case, let's take it at B. So it's equal to 0. I'm going to choose the positive convention for this scalar equation here. And when we think about it now, I've got my unknown fay here. How many inches over is it? From B? I think I had that right there. OK, so that's 20. So it's 20 inches over to that perpendicular distance. That's the perpendicular distance to the line of action of that force BY, or AY. Do I include FAX? No, it goes through B, doesn't it? So its line of action goes through B. There's no moment arm. So I don't have to worry about that one. Next piece I'll worry about again is the 40. Oh, quick question here too. Positive or negative in terms of rotation? It's going to be negative. We're holding it at B. That force AY, the way I have it shown, is this way. We'll solve for it. If it says negative, then it's going the other way. So I need to pay attention to that, though, in terms of my convention that I've chosen for this equation, this scalar equation. OK, then I've got my 40 And it's acting in terms of perpendicular distance. It will be same as the other one, 10 inches. Is that positive or negative? That's also negative. And then finally, I've got the 50. How far away is it acting? 16. Positive or negative? And when we plug and chug through this, what we find is the same answer that we did with sum of forces x. Same approach. Okay, so for my third equation, I've got to take a look here. And since both of them lie on the x-axis, when we think about that, I'm not changing any sort of y dimensions there. Everything I do is going to be the same. The 40 is going to be 10 away. That's the only one that actually I have to worry about there. Since I do that, since they lie on that x-axis, then my third equation has to be the sum of forces in the x direction, which one, when you look at it, it makes sense. We've just solved for by, we solved for ay. The only piece it's missing is the ax. And then we just do that just like we did in the last equation there, or what we did on Tuesday there. So we have a situation now where an alternative approach, and what we're going to find, it doesn't make a whole lot of sense here, but when we get into more complicated structures, it will make some sense there in terms of possibly using moment equations. The nice thing about moment equations is we can pick points where we eliminate forces. When you think about it, in terms of sum of forces y or sum of forces x, they're all there. They're all going to be summed in there. So if we have 2 or 3 unknowns, they're going to roll right up into that equation there. The nice thing about moment equations is I can pick points where I eliminate unknowns. And we'll keep that picture up there. And then as another alternative, we can actually just go to 3 equilibrium or 3 moment equations there. So as before, sum of moments at A were equal to 0. Sum of moments B, we just got done doing that one. So we can set up a third equation now by taking a point C, again, a point that we have some measurements that we can measure perpendicular distances and that sort of thing too. Now when we consider C, we'll note that FBY goes through C, so we're not going to put that one in there. We'll also note that the 40 goes through C, so we're not going to put that one in there. I am going to need to put FAY, FAX, and then the 50. Okay, so again, the FAX is at 10, positive or negative in this equation? Negative. I'm holding it at there. It's going to want to rotate me in a negative sense. Okay, the FAY now is going to be 20 inches. Is it going to twist me positive or negative? Negative. And then we have the 50. Similar to what we did there with the other one. I don't know why I want to keep leaving that there. Positive or negative? Positive. And that's the only ones that will contribute there. We'll set that equal to 0. Now we already know FAY, right? We just solved for that as 20. So plugging that in, we can solve for FAX like we did with the sum of forces in the x direction there. So when we use the 3 moment equations, the only restriction we have there is that the 3 points that we choose to do our moments cannot lie in the same line. Now actually you'll find that out because when you plug in, if you plugged in C, it was on the same line there, you're going to find out you're not going to get any information from it. It'll give you the same information as the other 2. Now just a couple of points to recall here. When we're doing moments and that sort of thing, if you use the cross product, it's important to make sure that you put in the directions and the signs for those forces there. So in this particular case, if I was doing a cross product from C to A, my FAX is actually going to be minus there, right? Because it's in the negative sense to my positive x. So when we use the cross product, we do put in the signs of the forces in the direction they're going. When we go to these scalar forms, when we go to the scalar equations, we have to set up a convention, and we have to think about the twist. So the force may look like it's going negative. FAY looks like it's negative or positive in this sense here. And if I were using the cross product, I would use the positive FAY in the determinant, solving for the determinant. However, if I go to the scalar equation, I have to pay attention to look at the twist there. And we'll notice that those twists change. When I was over here at A, the 50 was causing me a negative twist. When I go over here to B, the 50 is causing me a positive twist. So when we go to the scalar equations, basically we have to sit back and think about that twist. That's why we put this little sign there. We have to keep track of that twist. But again, if you go to the cross product, put in the values in terms of positive or negative based upon the sign convention that you establish. Does that make sense?
Yes.
Such an enthusiastic group today. Okay, we'll start off with the handouts. What we're going to do is talk about some of the special systems. And we'll kind of explain why we're going through that, because what we're going to find, there's handouts there too. Thank you. Oh, thank you. Okay, so we'll talk, this is I'm not sure it's actually in your book, so this might be a little separate section there we want to think about. But the reason why I'm bringing up the special force systems, we talked about these earlier when we were talking about basically the force systems. But the key thing I'm trying to get across here is that when we go to some of these special systems, what we're going to find is that we have less equilibrium equations available. We can only solve for a few things. So again, taking a look at a collinear system, so it's a column or something like that, or a pipe, where all of the loading is basically on that same line, that cool word collinear that we can impress our English major friends with. The problem with that is however, is that we only have one equation of equilibrium. Sum of forces in the y direction is already 0. Sum of moments is going to be 0. If I take a moment anywhere along that line there, it's equal to 0. So when we have a situation, a special situation such as the collinear, we're only going to be able to solve for one unknown. Now, we talked about concurrent. This is when we were doing equilibrium of a particle. And remember, we talked about that in the sense that the only equations we had available to us was sum of forces x and a sum of forces y. And the reason being is that if I take a moment, and moments have to be 0 everywhere, right? So if I take a moment at that point there where they all intersect, there's no moment arm. So it's automatically equal to 0, which implies that I can't use that moment equation to solve for something. So I'm only going to have two equilibrium equations available to me. And this will get important when we get into things like trusses, analyzing trusses and that sort of thing. We're not going to be able to find 3 or 4 forces at a particular point there. We're going to have to look for joints that only have 2 unknowns. Another one that's difficult too, or reduces our number of equilibrium equations, is going to be parallel forces. And again, what we'll find there is that we've got the sum of forces in the y direction, but the sum of forces in the x direction is already equal to 0. There's nothing going on in the x direction there. So in terms of solving for that, we only have 2 equations of equilibrium. The sum of forces in the y and that moment equation about the z-axis are coming in and out of the page there. So we can only solve for 2 things in that particular case there. So we're going to have to make sure, especially when we get into more complicated systems, of keeping track of these special systems there, because we're going to find that we don't have enough equations to get us through. Okay, moving on to, is it determinacy that's in your next? Okay. Now, what we're talking about in determinacy, what they mean by that word basically is can I solve for all of the unknown forces? Okay? So our general case, our general 2-dimensional case there, if I have a situation where, say, for example, I've got a pin connection and a roller there, basically I draw my free body diagram. What I have is 3 unknowns. I have my A in terms of force, magnitude and direction there, and then the By, since I know basically its direction based upon that support condition that I pull away from it. So my unknowns are 3. I have 3 equilibrium equations. I can solve for everything there. I should be able to, unless I've really screwed up somehow. Now, other situations we may run into, say for example we have a situation where we have 2 pin connections there. Well, when I draw the free body diagram there, I have to put in my unknown force and unknown direction at both of those points. So I've got 4 unknowns there, but again, if I'm doing this in 2 dimensions, I only have 3 equations of equilibrium. What that means is I can't solve for everything. But there's a little note there, but note we can solve for some stuff. If we think about it, if I were to take a moment at the A point there, this is some sort of a loading. We'll get to learn how to do that later. But note that at A, the AX and the AY do not participate in that equation, right? Because they go through that point. But also note that BX, since it happens to be in that same line there, also does not participate in that moment equation. So I can write a moment equation that includes this load and then an unknown BY in some distance. So I can solve for that, and I can do the same thing. I do my second moment equation, and that's why we like these alternative forms. I can go over to B, note that AX goes through B, but I can solve for BY, or AY. So I can solve for the 2 vertical components, and then my last equation be sum of forces in the x direction since they lie in that x-axis there. The best I can do is just note that AX plus BX has to equal 0. I don't know whether they're 0, they might be 100, whatever. But the key thing is I can get some information out of it. So when you see something that says it's statically indeterminate, that doesn't necessarily mean that you're stuck. It just means that you can't solve for everything on that. And what we'll find is when we get into other structures, we're going to be breaking them up and looking at various pieces. What we're going to be able to do is possibly go through situations where there's maybe more unknowns than we expect, but then start looking at other pieces, and then using Newton's third law, saying, okay, well, equal and opposite reaction there, I can go back and start solving for the other unknowns. Okay, and then the last piece we want to talk about is stability. And you'll have a homework problem on this. But again, this is something that we kind of don't talk about too much. We spend a lot of time getting you to learn how to calculate forces. But as engineers, you also have to understand whether that structure can stay there or not. I wondered why you're all looking like this. So there are situations, again, when the key thing, and this is why we say the free body diagram is so important. Draw that free body diagram. There's my supports, 2 rollers. Well, then that means I've got forces vertical or perpendicular to those surfaces. I end up having 2 parallel supports there. But again, if I have a load that has any sort of x component, think about the sum of forces in the x direction. Nothing there. I've got px, but I don't have any support to resist that. So this is a situation where it's considered a partial constraint, where basically the number of support forces is less than the independent equations of equilibrium. Now, we could solve for that if P was absolutely vertical there, then we can solve for it. It's partial, but again, we can go in and start solving for some pieces. But in this particular case, stability, we wouldn't want to put a building on that or something like that, unless it was in an earthquake zone or something. The next one we'll look at is what we'll call improper constraints. So that means there's enough unknowns there in terms of the supports, but they're not really situated properly. And this is a similar problem. We just add another roller to that. So what we find is that I've got 3 unknowns there and 3 equilibriums of equation, but the problem is that they're parallel. And again, I have that problem where I don't have the ability to resist anything in that x direction. So I have enough unknowns, but unfortunately, my unknowns are situated to, again, that special equilibrium case that we were talking about there. We don't have the ability to solve for that x direction there, and the thing will be a skateboard, basically. It'll just start taking off on us. And the other one that's a little harder to visualize most of the time is what we call the concurrent supports. And this is something that they actually experience a lot in dry docks. They dock a boat and that sort of thing, and it's got a weight there. But if all of your supports are set up such that they're providing the forces that all go through a single point there, well, think about if we added some load there to the side there. They look like they would resist, but actually there's nothing there to resist the moment. Take a moment about that point there, where all the forces are concurrent. Okay, well, moment's equal to 0 there, but as I add another load there, say I add a P to the side here, there's nothing available to resist that because none of these forces have a moment arm. So we have to be careful. This is the hardest one to see. So you need to think about that in terms of looking at those. But if they end up with all the forces being concurrent, you don't have moment capacity there. The thing will start rotating like. Got that?
Would those be considered equilibrium if they have a force on them? Like if that px force has no couple, but it doesn't have friction?
Yeah, if there's no px there, then it's in equilibrium, but it's not stable. So you've got to be a little careful.
I'm saying those ones as they're pictured in the free body diagram, those aren't at equilibrium though, in that.
This one is not. No, since there is a px there. This one actually is because I forgot to put the p in there. Yeah, you're right. But yeah, those 2 are not in equilibrium unless px is equal to 0. And again, they're in.
Force or something bringing it the other way.
Well, you're getting into chapter 8. We'll get there. Yeah, we'll eventually get to that point there. So, yeah, there are situations like that. But again, some of these cases, especially with the improper constraints, are something that's very real out there and people have to be careful of. And people, unfortunately, die because people don't think about how to set those up. Okay, so we talked about special force systems. What we're going to talk about now is a couple of unique equilibrium situations that we want to take advantage of, especially when we get into the more complicated structures. Okay, so the first one that we're going to look at is the equilibrium of what we call two force members. So we'll draw our engineering baked potato there. I'm going to put a couple of forces on this guy. Okay, so I'm going to put a force 1 on A. They're acting semi-horizontal there. And what I'm going to do is, again, since I have the power, I can put in my own coordinate system. So I'm going to choose a coordinate system such that x is parallel to that line of action. It's on the line of action. Now we're going to put a second force on that member at point B. Now again, since I've got this at point B and I've described a coordinate system like that, I can break my force 2 into components that are consistent with that coordinate system that I've established there. So I can break it up into an AX and an AY component there. Okay, so that's my free body diagram. And let's go through the equilibrium equations and see what they tell us. First of all, we'll start off with the sum of forces in the y direction. Okay, does F1 have a component in the y direction? No. Does F2 have a component in the y direction?
Yes.
Okay, so F2, y, anything else? Okay, so the right hand of my equation says 0. Okay, so what that's saying now at this point is that my force 2 cannot have a y direction. It has to be parallel to the line of action of F1. Matter of fact, we'll go so far as let some forces in the x direction. And what we find then is that the way I've got it drawn there, actually it'd be, well, let's be proper here. -1 equals 0, which says F1 is equal to F2x. So setting up the equilibrium equation like so, F1 is in the minus direction there, F2 is in the positive direction. Go through the calculations. That says that the x component now is equal to that. So equal in magnitude now, they're in the same direction. Final equation of equilibrium. Let's do a moment equation. And if I do it at A, does F1 participate? No? Okay. So what I'll get my pens are dying on me here. Okay, when I do a moment equation there, F1 doesn't participate. We've already decided that F2y doesn't exist. F2x has to be equal to the magnitude of F1. And what I find in terms of laying out an equation, that F2x times d has to equal 0. So what does that tell me? F2x doesn't equal to 0. We've determined what that is, so therefore d is equal to 0. So what does that say about my forces? They have to be collinear, same line. Yes, exactly.
So whoever drew your picture isn't very good?
Well, I drew the picture like that so I could prove to you through equilibrium that it has to be along that same line of action, same magnitude. So yes. So let's think about a situation where we have an angle that has a couple of pin connections. Okay, at a pin connection, recall if I pull that away, whether it's attached to the ground or attached to another body, a pin connection has two unknowns, right? An unknown direction and an unknown magnitude, or the way we like to draw it. Okay, so when I pull that object away from whatever it is, the ground and that sort of thing, I have my unknown direction and my unknown magnitude. So I display that in terms of an unknown x component and an unknown y component. How many forces are acting on that member? Two. That's the word you had. You're getting there. It's two forces. Again, it's an unknown. There's two unknown components of that force, magnitude and direction, but it's still a two-force member. If it's a two-force member, and we just got done proving that it has to act along that line of action, then what that's telling me is that I know the direction. Even though the member is not straight, if there's only two forces acting on that, then they have to be acting along that collinear line there, just as we proved here. Does that look familiar? Did we state that one other time? That's Newton's third law. So the nice thing about that is what that's telling me then is I've eliminated one of the unknowns there. I know the direction. The only thing I don't know now is this magnitude. And if I solve for this one, I got this one already because I know it's going to be equal, opposite, and on that same line there. So if I solve for F1 somewhere else, I've already got F2 solved for. I can continue, start looking at the rest of the structure there, start moving my way through the structure. This will be very important when we get into very complicated machines and frames and that sort of thing, because what you're going to want to do is look for these members. And they may not, like I say, they may not be nice straight lines like in trusses and stuff like that. They may be curved and stuff like that. Actually, we'll go through a curved example today. We'll see things basically that if we can recognize the fact that it's two forces, then we've eliminated that direction. We've got the direction figured out already. Now, all bets are off when we go to 3 pins and stuff like that. So 3/4 members don't necessarily work. But we will talk about that. So we'll look at 3/4 members. And again, I love my engineering baked potato here, so we're going to consider a body now that has 3 forces acting on it. And I'll draw its line of action. And then I'll set another force acting on it. And then we'll add that third force. Kind of looks straight. So that's my free body diagram for a 3/4 member. So let's consider this intersection here at F1 and F2. Now, if this body is in equilibrium, that implies that moments in the z direction, since I've got a 2-dimensional problem here and it's in the board, that the moments have to be equal to 0 everywhere. So let's consider taking moments at this intersection O, we'll call this of F1 and F2. And again, in terms of the moment equation, F1 will not participate, F2 will not participate, because there's no moment arms. What I have is F3 times some unknown distance, again. So that would be my D, that perpendicular there. But what I'm finding again is if F3 has a value to it, then what that's saying again is that D is equal to 0. What does that mean if they're equal to 0? If that D is equal to 0? Have to go through the same point. Or using our way cool word, concurrent. So what that says is if I have F1 and F2, I have those values in terms of a vector. So that means I know their direction and their magnitude. Then the direction of 3 I can establish because all I got to do is find that intersection where 1 and 2 go through. The only unknown I don't have is the magnitude. But I can solve for that by putting it into equilibrium, setting the other side equal to 0 there. Now we have to be a little careful because, again, going back to the special equilibrium case, since those are concurrent, then we're only going to have Fx and Fy, sum of forces in the x direction and the y direction, available to us. Moment equation's not going to help me in this particular case because they all go through the same point. Oh, back to pictures here. OK, so what we're going to do, not sure I'll put it up. Let's go ahead and look at the example problems. And I won't spend the time rolling the thing back and forth here so we can get through these problems there. We've got a frame, and we've got a set of loads on it. And what we've been asked to do is determine the forces, the reactions basically at A and C. OK, so as a first thing, and again, remember, you'll lose points if you don't do it. This is an equilibrium problem. We need to draw a free body diagram. I need to know where those forces are coming from. What is that called? So we'll consider drawing a free body diagram of that frame. My red, oh, there it is. OK. And I will set up a coordinate system here. So that's the free body diagram of my frame. Again, it's just the external thing there. Now I've pulled it away from A. So it's a pin connection. How many forces?
2.
How many forces? How many unknowns? Let's start off there.
2 unknowns.
2 unknowns, 1 force. We got to remember that because when we get into pins and start looking at structures and stuff like that, we're going to pay attention to that. So I've got a pens are dying. So I'm going to draw it in terms of the component form because we know we're going to probably throw it into a scalar equation there. So we've got those there. We've got the known force. I should have started off with that one, but we've got the 30 pounds out here. And then we've got a pin at C, which will have the same situation there. I'll have a y component and an x component. So it's an unknown force. Now, looking at that, how many unknowns do we have?
4.
Yeah. And there's nothing really tricky we can do. Equations of equilibrium in 2 dimensions are only going to be 3. Now, I can't even do that trick like we did with the earlier one there, where I did a moment equation to get the y component. Because again, if I took a moment equation here, I eliminate the y and the x, but I have an FCy with a moment arm, and I have an FCx with a moment arm, and then this. So I've got 2 unknowns there. I sum forces in the Y direction, I got 2 unknowns. I sum the forces. In the X direction, I got 2 unknowns. So not going to help me. I only got those 3 equations, but I still have 4 unknowns. There we go. What we're going to want to do is separate it. Now, where should we separate it? Well, what we want to do, what we want to do is separate it at a point where we know we can substitute those unknown forces. Now, if I cut it somewhere in the middle of the beam, what we're going to find when we get into beams, there's shear, there's moment, and everything else in there. But if we cut it at a pin, whether it's connected to the ground or connected to another structure, is still a pin. So my free body diagram of AB will now look like that. And what I'm going to do is I'm going to have those same set of forces there. Oh, and I need to get my coordinate system up. That one. So that doesn't change. I mean, that's still a pin connection. But I've got a pin connection down here. And I can do the same thing because it's a pin connection. I know it's an unknown force and an unknown angle, so I'm going to draw it in terms of its 2 component forms. Now the other thing we'll need in here is useful dimensions. And actually we don't need that. Now, anything noticeable about this member? It's a quarter of a circle, yeah. How many forces are acting on it? 2. Ah, there we go. So, we know that it's going to be acting at that angle there. And since this is a quarter circle there, I can even measure the angle from my axis system. I saw a hand go up. Question?
We don't have the forces of B on the original free body diagram?
We don't. And again, let's think about that. That's a really good question. I'm glad you brought that up. So why doesn't B, the forces at B, show up here? Again, it goes back to our definition of what a free body diagram is. It's the external boundary of something here. So we've drawn the external boundary here. Yes, the pin exists. It's inside. It's doing its job. But it's not external to this free body diagram, right? So that's a mistake a lot of people make, and I'm glad you brought that up. When we draw that, yes, there may be pins all over the place. When we do trusses, basically there's going to be pins all over the place there. But in terms of that external boundary, that pin is not external to it. It's part of the contiguous structure there. So it doesn't show up here. It only shows up when I actually pull it away from that body. When I pull it away from that body, then I have to substitute in what the portion BCD is doing in terms of a set of forces. And since it's a pin connection, it can only be that unknown force, unknown direction.
So since it's mounted, so forces A and C are mounted at 30 pounds as an applied force, is that why those are the only ones on the original free body diagram, because they're external?
This is external. I pulled the ground away from this one, right? I pulled the ground away from this one, and then the 30 is existing there. That make sense? So that's a really, really good point, because a lot of people start seeing forces showing up here in the middle there, and boy, it messes up the equilibrium equations in a hurry there. Only what's external going on here. So I'm pulling that away. I've not pulled B away from the structure. B is part of that structure there, so it's not doing anything. It's doing work in here, but we don't see it in terms of its forces.
Is that because you just consider this all one rigid body, so no action is really happening at that pin?
Exactly.
caused by the thing, yeah.
Exactly. So it meets all the criteria in terms of a rigid body, that it's not deforming there, it's not bouncing up and down and stuff like that. You'll get into dynamics and stuff like that. So it's basically in position, it's being held there, it says it's in equilibrium, so it's static, it's sitting there in a stationary sense there. So yes, it's working, but basically we don't see it because it's internal to that free body diagram that I've drawn there. Now, I go that step and start pulling away pins because I know what goes on at pins there. All of a sudden, by and bx show up. Note though, fax and fay will still be the same. If I solve for those, well, they have to be the same here, right? It's got to be the same for whether I'm looking at the whole structure or part of the structure there. So be aware of that too, that these don't change. If we solve for one of those components or both of them, then basically if I solve for my by and bx already. So it's going to be the same piece that I pulled away from the ground. What I'm doing here is now just simply removing that portion of the structure and substituting in now what that pin is providing us there. Okay, so we've gotten to that point, and what we found is that we can establish a direction for FA and FB, and actually we know they're going to be equal in magnitude, opposite in direction, and stuff like that. So I really only have one unknown here. But the problem is I don't have any load there. I've established the fact that they have to be equal and opposite each other, but I don't have any now load to be able to calculate with. So now I look at the other portion of the structure there. I'm going to take that part away. A very exciting structure there too, hard one to draw. Now, going back to what we did before, it's going to have that same support condition there. Getting towards the end of the lecture here. So I still have that portion that I pulled away from the ground there, that pin. And I've also got my 30-pound load now acting here. We've got our coordinate system up here. Now the tricky thing to be careful of here is that we've got to pay attention to Newton's third law. I've drawn an FBX and an FBY here. So when I go over to here, I'm going to put, this is FB, this is my pin here. But I'm going to need to put those in those opposite sense. So which way do I have those going? And when we get into more complicated structures, it's going to be important to make the fact that when you solve for one of these or the other, basically, you're going to have to apply Newton's third law. So if it's acting one way in one piece, it's going to be acting opposite in sign, same in magnitude, but collinear. But realize the fact that we also, looking at that other structure there, realize that we've established the direction of that already because I know it's a two-force member, which then says Newton's third law has got to apply here too. I know my force is going to be acting that direction or the other direction. We're not sure, but kind of looks like it'll be acting that way. But what I've done now, at this point in time when we look at this, is now I've eliminated an unknown. When we were at this, when we first started this, without looking at the direction there, we had the same four unknowns that we were dealing with in the entire structure there, except that we had it broken at B. But now, if I go back to this structure, portion of the structure here, realizing that I've got a two-force member, I've established its direction. I can come back here and say for a fact now that I know that the direction has to be on a 45. So now I have the relationship between Bx and By in terms of 45 degrees are going to be equal. I've eliminated one unknown. Now I can use my 3 equations of equilibrium and go ahead and solve for them. So we'll go ahead. And again, since I've established this one, it's still an unknown, but it's only one unknown. If I can go to C, I can save myself a little work here because I can solve for the 2, I can eliminate the 2 unknowns there at C, or the unknown force and unknown direction there, have one unknown, and one known. Oh, and the one thing I didn't put up there, there's my green. And again, my necessary dimensions there, I keep forgetting about my moment arms there. Question?
Just out of curiosity, before we do this later, but can you substitute FB right now with a equivalent FA at that point, since they're the same but opposite?
Yes, you could, yeah. So what we were asked is, can I substitute FB for FA? Sure, yeah, because we know that FA, it'll be a minus FA. But yeah, we can establish from this one here that FA is equal to FB, just opposite in sign. So yes, you're leading me there right to it. Yeah, what we're going to do is once we solve for that, we solve for F of A.
Okay.
So going back there, I forgot my dimensions there, but we take the moment there. I'm solving just for the by component there. So I can either solve for FBY or I can solve for FB times sine of 45 degrees, whatever you want to do. Yep, and 45 pounds. Yep. So it's going to be acting down, which makes sense when you think about the lever there. That's going to want to twist me that way, so I need something to twist me the other way there. So again, think about that. Is it taking care of the twist, not letting my body rotate off into space? And then I can solve for the other components. I generally like to use f of x and f of y and stuff, because then I don't have to worry about doing those multiplications to get those moment arms and perpendicular distances. But there'll be cases where that is not. Oh, hold it. I should solve for y first. Since I've got the y component, although I know fbx and fby are the same there. So I've got the minus 45 there. And it'll be acting. So I consider my 2 points there. I've got the 45 that I just solved for there, the by component. I've got my 30 acting down. And then I've got my cy drawn in the proper sense there. So it turns out to be a positive 75, which implies that I picked the right direction there.
Shouldn't your arrow for positive be pointing up and not to the right?
Sorry, I started off with fx. Yes, thank you. There. Good catch. And then my next equation is going to be the sum of forces in the x direction. Now I'll get the arrow going in the right direction. And then noting the fact that I know my bx and my by components basically are equal, since it's a 45-degree angle there. So my fbx will be 45 acting in this sense. My fcy is acting in the opposite sense, and I solve for that. And it comes out positive, which then implies I chose the right direction for it, which is actually in the negative sense. And then Again, if I'm looking at a pin, I'm really going to be interested in what the full load is on that, not the X or Y component, that sort of thing. So we want to solve for the full amount there. And it'll be acting in the minus 45 degrees. And then the full load then acting on that pin C there, or at that support there, is going to be 87.5. And going through the calculation there, rise over run, in this particular case, we'll find that it's about 60 degrees then in terms of the force acting there. And we'll dive into the next problem. So we're going to see that a lot when we start doing frames and that sort of thing, where we're going to basically want to take it apart at the pin. It's no different than taking it away from a pin support on the ground. We substitute in the unknown components of force. But when we walk our way through, we have to pay attention to the Newton's third law. If we solve for it in one direction on one piece, when we look at the connecting piece, equal, opposite, and collinear. So we'll look at 469. When we look at, we'll see that it's going to be a 3-force system. And of course, before we do anything, we're going to draw a free body diagram. Force out there so I can see it. Okay. So at A, we've got a roller support there. We know then that force is going to be perpendicular to that surface there, which is shown as horizontal. So my force will be vertical. I have my 300-pound force there. At 45 degrees. And then I've got a pin connection at C, which I again will show, at least for the moment, in terms of X and Y components, establish a coordinate system. And then get in some necessary dimensions here. What is that in? Is that in millimeters? That's 300 newtons. Okay, so I've kind of given it away here in terms of talking about it being 3 forces there. We've got a force here. We've got a force here. And then we actually have a single force here. I've just shown it in component form. So 2 of the forces I already know directions to. This one's perpendicular, so its line of action is doing this. And my second force is at 45 degrees, so it's doing something like so. which implies then that the force here has to go through that point. Let's see if I can draw that without drawing too many. Which implies then my force at C has to follow that line of action also. So what I've done is simply eliminated an unknown quantity here. I've established the relationship between Fcx and Fcy. So let's establish a couple of things here. So that angle we'll call from the horizontal will be alpha. Oh, yeah, we need to establish a few things here. Okay, so when I think about this, is that this is at a 45-degree angle here. I've got this from this to this point here. It's going to be 150 plus 250. So my run, forgot, this is the angle I'm looking for here. So my run is going to be 150. I'm going from there to finding an intersection with this vertical force here. So my run in terms of the tangent equation will be 150. And then by virtue of the fact that this is going to be 400 from this point to the point of the vertical, then that implies that that will also be 400. And then to get myself down to C, I've got to continue there in terms of the 300. So my rise will be 300 plus the 400. So everybody see that before I go on? OK. Again, we're getting back into geometry here. OK, we know this is a 45-degree angle, right? So the distance from here to that vertical, where it will eventually intersect, is going to be a leg of 400, right? Comfortable with that piece? Well, then that implies if it's 45 degrees, that's going to be 400. So the rise for my angle here has to be 300, which is the height of this structure, plus the 400 to the point of intersection, right? Comfortable with that? I see a lot of heads kind of going, oh. And then my run, since I'm going from C, is only going to be this 150. That making sense? What I'll do is I'll post this solution too so you can go through it. But what we'll find then is that it'll be about 77.9 degrees, about 78. So we've established that line of action for C there. So I can go into my equilibrium equations. Are we doing on time there? I'm cutting it short. So just in terms of summing forces in the x direction, I'll have two components there, the 300 times the cosine of 45 degrees. If I measured it from there, actually that should be the sine, but it will be the same regardless. That'll be 212.1 newtons. And then when I want to solve for f of c, I can take advantage of the fact that do that right.
Would that be negative?
It'll be positive because I've drawn it in that, and I chose the right sense. So again, what the equation tells me is then I've corrected it in the right sense there. Where I'm going with that is, I just want to make sure that makes sense to me there. Yes, okay. By taking virtue of the fact that I know that since the long leg basically is fc there, the magnitude of that times the cosine will give me fcx. Basically, I simply can plug it into this equation, just rearrange it there, and solve for directly for f of c then of 1,012 newtons. And then, yeah, we'll go ahead and draw the. And then summing forces in the y direction there, I've got my unknown f(a)y there in a negative sense. I solve for fc, so I'm going to take fc times the sine of that 77 degrees, so I'm getting that vertical component. It's in a positive sense. And then my 300 again is going to be that same value of 212.1 degree newtons there. It's acting negative. And then we can solve for that roller reaction there of 778 basically newtons acting down. So now a couple things. What we did is we took advantage of the fact that we knew that these intersected. Note that you can just simply use the equations of equilibrium. You can do moment, two moments, sum of forces x, sum of forces y. You can do that same approach. So I'm not saying that we've eliminated that. This is just showing you yet another way of solving an equilibrium problem in terms of three forces. So I'll post that. I think I will post both solutions for this one. That way you can kind of see how both of them work, basically, and understand them. All right, have a good weekend.